Good morning to everybody. Welcome to the mass transfer course. Today will be lecture 13 and this will be the last lecture of convective mass transfer and mass transfer coefficients. So in previous lecture we have discussed different theories to calculate the mass transfer coefficients. These are film theories, penetration theory, surface renewal theory and boundary layer theory. And we discuss what are the demerits and merits of the different mass transfer theories. Today we'll discuss about one interesting thing, that will be that momentum, heat and mass transfer analogies. Because if you see, every time I am giving the example that you have studied already this thing in heat transfer, you have studied this concept in fluid dynamics, similar concept is in mass transfer. Now what are their analogies? But now if you see transport of momentum, heat and mass in a medium in laminar motion, let us discuss with laminar, then we will discuss with the convective. Okay, laminar motion are all diffusional process, okay, and occurs by similar mechanisms. Means when there will be pressure difference, fluid will flow from higher pressure to lower pressure, and when there is a temperature difference, so heat will flow from higher temperature to lower temperature, and if there is a concentration difference is there, mass will flow from higher concentration to lower concentration, and these are all driving forces. And correspondingly we have seen that whether proportionality constant is there for heat, that is the heat transfer coefficient, and for mass it is mass transfer coefficient, and reciprocal of coefficient is called resistance. Okay. And these three basic laws in this connection, that is Newton's law of viscosity, that governs the transport of momentum. So momentum we know m into v, mass into velocity, that is the momentum. Fourier law of heat transfer, heat conduction and Fick's law of diffusion can all be expressed in a similar form. How? Let's take the Newton's law for momentum flux, tau, the force per unit area, okay, shear stress, okay, that is equal to minus mu into du x by dz. Now if you consider this in terms of momentum, then if you divided by rho and multiply by rho, then it will be d rho into x and mu by rho, that is nu, that is kinematic viscosity, or it is called momentum diffusivity. Okay. So this is rho into, but rho into ux means this is the momentum per unit volume, because rho equal to kg per meter cube into meter. So this is the mass per unit volume into x. So this is the momentum flux per unit volume. Okay. Or it is called volumetric concentration of momentum. Okay. So what is the change of volumetric concentration of momentum? That is proportional to your shear stress or force per unit, and this is called viscosity or momentum diffusivity. It is called the momentum diffusivity. This is called nu rho by nu. This is called momentum diffusivity. Okay, and rho into x is equal to volumetric concentration of momentum, because momentum per unit volume in the index. Now, Fourier law of heat flux, what is this? This is equal to Qz in z direction minus k dt. Now, this is temperature, but if you see the heat flux, what is heat flux? It is rho Cp into T. So, if I multiply into rho Cp, then I have to divide it rho Cp. Okay. So, rho Cp into T, if we take, that is mass per unit volume. Okay. So, kgCp into T, that is the heat content of a particular volume, and rho, this is heat content per unit volume or volumetric concentration of thermal energy. This is called volumetric concentration of thermal energy. Okay. So, thermal energy per unit volume. Here, momentum per unit volume. Okay. This is thermal energy per unit volume. That change equal to alpha. What is alpha? Alpha equal to, then alpha will be your k by rho C. And this is called also thermal diffusivity. So, in case of fluid dynamics, this is the momentum diffusivity. In case of heat transfer, this is the thermal diffusivity, but both are diffusivity. And in Fick's law, that is Na equal to minus dAV dCA by dZ. So, in this case, what is Ca? Molar concentration, moles per unit volume. Okay. So, this is the molar concentration, this is the volumetric thermal energy per unit volume, this is the momentum per unit volume, this is mole per unit volume, automatically. And dAV dG, this is also, we know the diffusivity. Now, what is the unit of the diffusivity of dAV? We know, that is, we know meter squares per second. And you know that what will be the unit of momentum diffusivity? That all will be also meter square by second, and this will be also meter square per second. So, all diffusivity unit is either it is momentum flux or heat flux or mass flux. Diffusivity unit is meter square per second. So, that's why it is the similar fashion, that's the analogy is there. And in 7 or 8 semester, you will study the one course is there, that is the transport phenomenon. And here there you will study all this thing in details. Transport phenomena is nothing but a transport of momentum, heat and mass, and how these things are taking place. That integration getting part of this thing you will learn. See, already you learn the fluid dynamics, heat transfer. Now you are learning the mass transfer, and then combination of these you will learn the transfer, how these are. So, but you should think means that for laminar flow, all are the similar mechanisms. So, because what is this is the content, momentum per unit volume, this is heat energy per unit volume, moles per unit, and this nu alpha, these all are diffusivity. This is momentum diffusivity, this is thermal diffusivity, this is the mass diffusivity. and all have the unit meter square per second. Now let's see how it is coming. Okay, but it is for laminar flow. So if you take the momentum flux, tau equal to mu into du by dl, tau equal to force per unit area. Force means, you know, neutral kg, m into a acceleration. So m means kg, acceleration meter per second, velocity, change of velocity meter per second square per meter square. So this will be kg per meter second square. So tau kg per meter second square into mu du equal to m by s meter per second, dl length 1 by m. So it will cancel out. This will cancel out. It will, so mu equal to kg per meter second. This. Okay, now tau equal to I divided by rho nu. This is the momentum diffusivity, and rho into u into, okay, rho is the momentum per unit volume. So change of momentum per unit volume, that is the rho u, and this is the your kinematic viscosity. And what is the unit? If you see, mu by rho kg per meter second, rho equal to meter cube, kg per meter cube. So meter cube will go up. Okay, kg, then meter the square, then unit of knee is meter square per second. Momentum diffusivity unit is meter square. Now let's see for the heat flux. For heat flux, Qx is equal to minus k dt dx. Okay, what is Qx? It's a flux joule per meter square second. Okay, K thermal conductivity, and this, if you take the dt, that temperature change is K, change of the x length, that is meter. So this will cancel out. So K will be joule per meter second by Kelvin, and joule per second, that is work W by mt. Or you can keep this one. Now what will be thermal energy per unit? The rho Cp into T. It is the thermal energy. Okay. So if I multiply with this, then I have to divide by K this, and this is equal to alpha, and this is the thermal energy per unit volume. Now what is alpha? Alpha will be K into rho Cp. K I know, joule per meter second Kelvin, rho kg per meter cube, Cp what? Energy content joule per kg per degree Kelvin. Okay, so and this will cancel out, kg cancel out, joule this can meter cube. So unit of this alpha is meter square per joule, and this is the thermal diffusivity. Okay, and for mass flux, N equal to minus dAB dCA dZ, and this is flux kilomole per meter square second, dAB kilomole per meter cube concentration by 1 by Z, it will cancel out. So dAB is meter square per second. So this is the molecular diffusivity, and unit is meter square. So all these processes are taking place in similar fashion. So same laws are applicable here, and that's why there is some similarities, isn't it? Now this is for your laminar flow. Now what happened in turbulent flow? In turbulent flow, similar equation used to express the rate of transport, except that eddy diffusivity is included to account the contribution of eddy terms. So we had, if you don't neglect, we had tau minus nu d rho ux dz. So this is the molecular diffusivity nu, and corresponding, because of this eddy, the eddy diffusivity term will come. Okay. Similarly, for heat flux, this is the laminar, that thermal diffusivity, and corresponding the eddy diffusivity of heat. This will be rho into similar. And for mass flux, dAB is the molecular diffusivity, then En, okay, whatever this thing, that eddy diffusivity or mass, that will come. So this term, and that will be the flux. Actually, here determination of nu, alpha and DAV is easy. You will get, because you know viscosity, you can determine from this, you can viscosity by density, alpha k rho by rho Cp you can take. DAV also it is possible. Now you know how to calculate this. But the eddy diffusivities of momentum, heat and mass, it is difficult to determine. And so because of that, we use the mass transfer, because it is not. So this is also a similar fashion is coming. So from this understanding, some interesting conclusion came. Okay. So what is this thing? Three scientists did three. One is Reynolds, Prandtl, and Kuhlmann. Already you have learned this thing. Reynolds number, you understand what is important in heat transfer, mass transfer, and fluid dynamics. It is very important number, and this is developed by Reynolds. Okay. So what he made the statement? This Stanton number heat. What is Stanton and Nusselt number by Reynolds number by Prandtl number? This is equal to friction factor by 2. Okay, they have seen for laminar flow that this Stanton number equal to friction factor by 2. Okay, and then Stanton number similarly they made for Stanton number to the mass. What will be the Sherwood number, Lorentz number in Smith number? That is also will be the F by 2. See, if this equation is valid, then calculation of heat transfer coefficient and mass transfer coefficient will be very easy, because friction factor, if you can calculate the friction factor, that you know how to calculate the friction factor in pipe flows. But keep it in mind, Reynolds, it is applicable for transport in pipe flow. So this is applicable in pipe flow. Okay. So that is your thing is coming, Stanton number to the Stanton number for heat transfer, that will be friction by 2, F by 2, and Stanton number to mass, that is Sherwood number, Reynolds number into Smith number, that is equal to F by 2. So if you can calculate the friction factor, easily you can calculate the mass transfer coefficient and heat transfer. So this is good. Okay. And it has been seen this relation is okay, but it does not have the very much accuracy. Then the Prandtl, he made another analogy, that is in pipe flow chain, the Stanton number height, that is friction factor by 2 by 1 plus 5 root over F by 2 Prandtl number minus 1. And similarly, Stanton number for mass transfer will be F by 2 plus 1 plus 5 into F by 2 Smith number minus 1. So here they made this thing in such a way. So they made this thing in such a way that as they bring this Prandtl number, because for heat transfer Prandtl number is applicable, and for mass transmission, so according to they introduce this thing. So this analogy is far better than that Reynolds analogy. And if you see, interesting point, if Prandtl number equal to 1, okay, if Prandtl, that term will not be there, so then Stanton number will be, so that term will be not means Stanton number heat equal to F by 2, so this is the Reynolds number. Again, if Smith number equal to 1, then Stanton number mass, that will be F. So Reynolds, this statement, it is applicable when the Prandtl number and Smith number equal to 1, then this Prandtl analogy will be the Reynolds analogy. But here, with this thing, you understand, we are correlating between fluid dynamics, that is the most important, the friction factor. With this, the important parameter in heat transfer is heat transfer coefficient, and in mass transfer. This thing we are getting, this what are the values. So, and these are the two analogies, and thereafter another analogy came, which is very accurate. And already if you see in your equation, we have used in mass heat transfer, so you have used this one, and we have seen in mass transfer also. So that is Coulomb analogy, that is JH, Coulomb factor. This is Stanton number high into Prandtl to the power 2/3. This is the Coulomb factor for heat. So then Stanton number, Nusselt number, Reynolds into Prandtl into 2/3, so 1/3. This equal to 0.023 into Reynolds number minus 2. And JD, okay, that is JD means diffusion, okay, mass transfer, Stanton number to the mass into Smith number 2/3, so this will say root number, that is also same. And it has been seen that this correlation analogy, Coulomb analogy, is much accurate than the Reynolds analogy and Prandtl analogy. But here, what we are trying to understand is, there are three transport processes: momentum, heat and mass, and these are very similar fashion. Their governing equations are very similar, and although we have studied separately fluid dynamics, heat transfer and mass transfer, but their processes are same. The basic origin of this process is similar, and after in 7 or 8 semester you will study another fundamental of this, that is transport processes. There also you will deal with more about how these things occurs. Okay. But here if it is interesting to know that in fluid dynamics, if you can calculate the friction factor, then you can determine the transfer coefficient and mass transfer coefficient from Reynolds analogy and Prandtl analogy. But in Coulomb analogy, it depends on the friction factor. It is relating to your Reynolds number, that is more reliable. Reynolds number, then you can calculate the Nusselt number. If you calculate, then you can calculate the heat transfer coefficient. If you can calculate the Serud number, then you can calculate the mass transfer. And that is required in your convective mass transfer. To calculate the flux in turbulent flow, you need the mass transfer. That is the most important number. And once you can calculate, other things are very easy. So this is all about your convective mass transfer. Hope you understand this thing, and we'll make one interaction session on this convective part. See, convective fluid dynamics is very abstract thing. You have to think, your imagination power should be very high. Similarly, because convective or boundary layer thickness, this is a concept. You can understand, you cannot visualize this thing. 1 millimeter thickness, isn't it? So you have to understand this, you have to visualize, the imagination power should be high, and then it will be very easy. So, but keep it in mind, convective mass transfer, when I am increasing the velocity, nothing, we are reducing the boundary layer things. But what is quantification of this thing is important. It is conceptually, it is okay. If you increase velocity, boundary layer things will. But what is this value? That is very important thing, because if mass transfer coefficient is high, very high, then your flux will be very high. So always we have a tendency, or we will try to increase the mass transfer coefficient so that we can increase the flux. And if we can increase the flux, then we will get better separation in a smaller component. So thank you for your attention. Have a nice time.